We're talking about asymptotes today and how to find them algebraically. So if you look at a graph like this one we have here, we can see that there are some asymptotes. Do you see that right here, this function gets really close to 0 but never actually touches it? That's what we call a vertical asymptote because it's a vertical line. And then do you see how here at y equals 0, it also gets close to y equals 0 but doesn't touch it? That's what we call a horizontal asymptote because it's approaching that number and getting really close to it. Asymptotes are invisible. You usually won't see them unless you have an older graphing calculator. Every so often the older graphing calculators will graph your asymptote, but typically they're invisible. So how do we find asymptotes? Well, first we're going to talk about vertical asymptotes. We're going to talk about how we spot a discontinuity. Remember, there are two things that are illegal in math. We can't divide by a negative number, or divide by 0. We can't divide by 0, and we can't take the square root of a negative number. We can't get that to right. So if any of those things are happening, we have a discontinuity, right? We have some domain restrictions on our function. Now, if we have the square root of a negative number, what happens, if you remember, is we have something like x is greater than 1 is what our domain ends up being. And so what that means is that this function only exists over here, right? The function doesn't even exist when x is less than 1. So there is no, oh, you can't even see that because of my big head in the way. So there you go. The function doesn't even exist over in the yellow. It only exists in the red. So say, the function is like this, right? So in that case, it's just a domain restriction, meaning that the function isn't there, okay? But if you remember, when we divide by 0, a lot of times we get something like the domain is all reals except x cannot equal 5 or something like that. Well, what that looks like on a graph is that you have this function. Here's x equals 5. And you have this function, and it's getting really close to 5 on both sides, but it doesn't actually touch 5. So when you're going to have an asymptote, it's when you're going to be dividing by 0. Okay? So typically our discontinuities are going to happen whenever we divide by 0 or when we take the square root of a negative. But remember, square root of a negative takes out a huge chunk of the graph. It says we can't have anything in this graph for a lot of places, right? But dividing by 0 really just takes out one number usually, or two, depending on what the factors of the bottom are. So it takes out those two numbers. That's where we're going to have asymptotes. We might have an asymptote there, or we might have a hole. So let's take a look at that. So we actually have three different types of discontinuities. Remember, we have a hole, an asymptote, or we also have a jump. Remember that a hole is considered a removable discontinuity, and asymptotes and jumps are considered non-removable discontinuities. So basically a hole, remember, looks like this. You're going along in the function, then there's a hole, and then it just keeps going. An asymptote looks like this. The function is going, and then all of a sudden it just goes to infinity, and then over on this side, it does the same thing. It could go that way, or an asymptote can be even. We'll talk about that. An asymptote can be even, and it can go like that as well. And then a jump looks like this, right? So the function stops, and then it jumps. So the way we're going to look at this is we're going to say a hole, the limit, okay. We find a discontinuity whenever we're dividing by 0. Okay, that's how we know we have a discontinuity. Any numbers that cause us to divide by 0 are our discontinuities. Okay, so then we have to decide, is it a hole, is it an asymptote, or is it a jump? Now, typically it's not going to be a jump. I'll just tell you that. Very rarely is it a jump. Typically it's going to be a hole and an asymptote. So we look at that and we say, all right, what's the limit as x approaches this number? Remember, limit is just saying as x gets really close to this number, what is y doing? Okay. For a hole, the function is approaching this number on both sides. So y is getting really close to that number on both sides, which makes sense because it's a whole. If you have an asymptote, the limit as x approaches that number is going to be infinity or negative infinity, right? Because if I'm getting really close to this number, my y values are getting huge. So in this case, the limit as x approaches this asymptote is a positive infinity, right? Because as I get really close to this asymptote, the y values just go crazy. So the limit as x approaches this number is positive infinity. So for an asymptote, your limit is either going to be positive infinity or it's going to be negative infinity. As it approaches a whole, it's going to be a number. We're going to approach the other part of that whole, or the y value of whatever that whole is. So this is actually going to be a number. And then a jump, the limit as x approaches this number is actually not going to exist because it doesn't approach the same number from both sides. So that's all you need to know about limits for right now, is that it doesn't approach the same number from both sides. So this one, say, is approaching 3. This one is approaching 5. So the limit just doesn't exist. So how do we know if we have a whole or an asymptote? Well, again, so we look for a discontinuity wherever we're dividing by 0. So the first thing we do is we look to see where we would be dividing by 0 and then decide whether it's a whole or an asymptote. So when I look at this function, this one is luckily already factored for me. And I see that I have two numbers on the bottom that would cause it to equal 0, right? I said each of these factors equal to 0. And I say I have a discontinuity. Let's see, x cannot equal 3, or, that's a really ugly 3, let's try that again, 3, or negative 1/2. So those are the two numbers that it can't equal. And then I look and I decide, are these wholes or are they asymptotes? Well, what I notice is that if I put in 3, I notice that if I put 3 into this function, I would have 0 times 5. So the whole top would be 0, right? Because this is 0. So I notice that this would be a 0 times who cares what that number is, right? Over 0 times who cares what that number is. So I'd end up with a 0 over 0 if I plugged 3 into this. And that is the indication that I have a whole. If I plug the number in and I get 0 over 0, what it tells me is there's a whole in the function. If I plug the number in and I get something over 0, like if I plug in negative 1/2 to this function, let's plug in negative 1/2, I get some number here, right? I get like 3 halves, and then I get negative 3.5, which is negative 7 halves. So that's just some number, right? Here's some number over 0. Because if I put in negative 1/2 down here, I'm going to get 0. This tells me I have an asymptote. So I have a whole anytime if I plug the number in, I get 0 over 0, then it's going to be an asymptote. I mean a whole. Oh my goodness, it's going to be a whole. If I get 0 over 0, it's going to be a whole. And then what I do is I look at that and say, wait a minute, here's an x minus 3 on top and an x minus 3 on bottom. I can cancel those out, right? They cancel each other out. And so this function simplifies to x plus 2 over 2x plus 1. And this is how I know that there's a whole there, because I can just cancel out the factor that created that discontinuity, right? There is a discontinuity at 3. And I can cancel that factor right out. And now I have a different function, right? This function and this function actually look the same. They actually behave exactly the same. The only difference is this one has a whole at 3 because of this factor right here that we can cancel out. So this one is going to graph just like this function, but it's going to have a whole at 3. So I know that this one has a whole at x equals 3. That's the x coordinate of the whole. And then I need to find the y coordinate of the whole. Okay, so basically I need to find the limit as x approaches 3. And all we have to do is we simplify it. We simplify those out. And then we plug 3 back into the function. Okay, because that tells us this function over here behaves exactly like this function. The only difference is this has a whole at 3 and this doesn't. So if I plug 3 into this function, it'll tell me exactly where that hole is. And it means that instead of being defined there, there's just a hole. Okay, so if I plug 3 into this reduced function, I get 5 over 7. So I get 5/7. So the hole for this function is at 3 5/7. Now we can find the vertical asymptote, I believe. Yep, I have that same function. We'll find the vertical asymptote on the next slide, but that's how you find the hole. Okay, so let's look at the next one. Again, I have a hole anytime I have 0 over 0. The easiest way to check these, or the easiest way to start with these, is always to factor the top and the bottom, because it's just so much harder to work with when they're not factored. So let's go ahead and factor the top and bottom. So what multiplies to -14 and adds to -5? That's going to be 7 and 2, so x minus 7, and x plus 2, so that factors the top. And then I can pull an x out of that one, and I get x squared plus 5x plus 6. So what multiplies to 6 and adds to 5, that's x plus 2 and x plus 3. Okay, so this is, oh, and I don't want to forget that x right there because I pulled an x out of that to begin with. So this is the function. I just rewrote it factored. Remember, it just changed clothes, same function, just different outfit. So now I have to decide, okay, what is a hole and what is an asymptote? The very first thing I'm going to do is I'm going to look for a discontinuity. I'm going to say, where is this function undefined? Well, that's anywhere that the denominator is equal to 0. So the denominator is equal to 0 at x equals 0. It's also equal to 0 at x equals -2 or x equals -3. Each one of those is a discontinuity. So I either have a hole or I have an asymptote. Okay, because we're not dealing with like radicals or anything that could have a jump. So we either have a hole or we have an asymptote. We have to decide which one is which. Now I look at this, if I plugged in 0, I would get a number over 0, right? So this makes that a vertical asymptote. If I plugged in -2, I would get 0, because if I plugged in -2 here, I'd get 0 times that, and that's 0 over 0. That makes that a hole. If I plug in -3, I'd get some number over 0, so that makes that a vertical asymptote. The other way you can find a hole is I can see what factors have in common, or what factors do they have in common. Well, this has an x plus 2 in common, so I know that's going to cancel out. Since it cancels out, it creates a hole. Okay, so I know I have vertical asymptotes at 0 and -3. I have a hole at -2. So then I'm going to go ahead and simplify this. I'm going to reduce the function. I'm going to cross out the things they have in common. And I remember that this first function behaves exactly like the second function. This function and this function look exactly the same, except that this one has a hole at -2 and this one doesn't, because I've canceled out that factor that's a problem. So now to find the rest of the hole, I can just say, hey, where is this function when x equals -2? What is that at? And it will tell me the point where this one has a hole. Okay, so I put -2 back into the function. So I have -2 minus 7 over -2 times -2 plus 3, which is going to be -9 over -9 over -2 times 1, which is 9 halves. Okay, so I have a hole at -2, 9 halves. It's very important that when you're writing the coordinate of hole, we have both coordinates. All right, I'll make another video showing holes and vertical asymptotes.